Hello, all you fine math folks out there. We're on question number 25 of the 2002 Fermat paper. So, this should be probably the hardest question on the contest. They usually try and order them so that the harder questions are at the very end, and then the questions sort of ramp up in difficulty. Of course, it's all depending on what you're more comfortable with. I find a geometry question at 24 is a lot harder than, say, a counting problem for 25, but to each their own. Here we are with question number 25, and I guess it actually sort of is a geometry question. The lengths of all 6 edges of a tetrahedron are integers. The lengths of 5 of the edges are 14, 20, 40, 52, and 70. The number of possible lengths for the 6th edge is... Okay. So we have 9 out here in front, which is very odd, and then we go 3, 4, 5, 6. Usually, I guess they order them by numerical increase, but the 9 out there is really sort of throwing me off. Okay, well, enough of that. So we have a tetrahedron, so we have to sort of stop and imagine, okay, what's a tetrahedron like? It's a good idea sometimes to draw a picture of a tetrahedron and say, okay, here we've got this, this, and this. But as I occasionally try and point out, it's also a good idea to bring props, especially if you're really bad at visualizing things in 3 dimensions. So I just happen to have sort of a Rubik's tetrahedron here to help me visualize. We're not going to be doing any Rubik's style stuff here, but I have a tetrahedron. And so I have 1, 2, 3, 4, 5, 6 edges. Now obviously this is sort of a regular tetrahedron, but it can still help me visualize things if I need it. So I could imagine, okay, maybe this will be 70. Could this be 20? Could this be 14? What sort of sides can we have? And trying to figure out the arrangements of the edge lengths, I think, is the real key to this problem. Because they're talking about possible lengths. So that means some lengths that we pick, so maybe the 6th length is, I don't know, another 40 or something. There might not be a way to construct a tetrahedron that way. Okay, obviously, with the way the question's being asked, there is a limit to the number of things the 6th edge can be. And to me, that makes the connection back to triangles. If I look at my tetrahedron, I see it's got triangles all over it. Any 3 of the edges together form a nice little triangle there. And there's certain limits to what edge lengths can form a triangle. So I think hiding in this tetrahedron question is an application of what's called the triangle inequality. So suppose you didn't bring your Rubik's tetrahedron. I think it's called a Pyraminx, for those of you out there who'd like to own a copy. For those of you who didn't bring one, we can actually just draw a picture of a tetrahedron. We use dotted lines to show that we're sort of peering in through the middle, and that these are sort of invisible and at the back. Okay. So each of the 4 sides is a triangle. So there are limits to the lengths which can come together and form a triangle. Okay, so what do I mean by that? If I'm looking at a triangle here, and I have side lengths A, B, C, well, the limiting factor is called the triangle inequality. It's actually a series of inequalities when it comes to triangles, but basically, A plus B has got to be greater than C. Think about it. If we were talking about 8 here, and we had a 2 here and a 1 here, there's no way the 2 and the 1 can meet to form a triangle. We're sort of stuck. In the same vein, B plus C is going to have to be greater than A, and A plus C is going to have to be greater than B. So these three together form the conditions that we must put on a triangle. Notice if we had equal to, maybe we had an 8 and we had a 5 and a 3, they're going to come together, but it's going to lie flat against the line. That's not really a triangle. That's what we call a degenerate triangle. Okay? Now, this can usually be summed up very quickly because, I mean, notice if C is the longest side length, then these last two statements are obviously true. So another quicker way to write the triangle inequality is to say the sum of the two shorter sides must be greater than, not greater than or equal to, just greater than the longest side. Okay, so that's our condition there. And I think that's going to limit which triangles, which of our edges can come together to form certain triangles on our tetrahedron. Okay? So if we redraw our picture of our tetrahedron, we might say, okay, well, it doesn't matter which side we place first. So you may think I forgot the dotted lines. No, now we're looking at the point on top and everything's sloping away. Anyway, we might say, okay, well, you know, maybe 14 is here. That's the first one we picked. If I put a 20 here, what can this other side length right here, the one that I'm about to highlight in blue, what can that side length be? It's got to be less than 14 plus 20. These are definitely the two smallest sides, right? So this blue one has to be less than 14 plus 20, that's 34. Well, none of our other side lengths are less than 34. So either this is our mystery extra side length, or we can't form a tetrahedron that has 14 and 20 together. Okay? So those are the considerations we have to think about, and this is how the triangle inequality is going to help us answer this question. So we have six lengths, 14, 20, 40, I think it was, 52, 70, and x. I'm just going to double check, and x is going to be our other side length. And so using the triangle inequality, I expect to get other conditions as to, oh, x has to be less than this, greater than this. And yeah, so I got the other numbers right. And so that'll limit the possible values for x. Okay. So if our blue one is x, then, well, actually, if we just redraw our triangle anyway, or our tetrahedron anyway, any side that I pick, let's say this thicker one here, it's going to form a triangle with two of the other edge lengths, and it's going to form no triangles with this final edge length. It's left out. Okay? So, if I want to, let's say, put x there. Actually, no. I think it might be better to talk about this left out side as well. (14) and 20 either go with an x, or as I already remarked, there's no way to make this side length work. So either we have 14, 20, and x form a triangle, or 14 and 20 form no triangles whatsoever, are opposite. Okay? because none of the other possible values other than x can possibly be less than 34, and that would mean we don't form a triangle here. Okay? So either we do have a triangle here, or we have a 14 and 20 is left on the outside. So we'd sort of we get 14 here, and then we'd have 20 here. So that's the idea. So these are two different cases that we can examine. So if we have 14, 20, and x, let's just take a look at that first case. 14, 20, x form a triangle. Alrighty. So we'll draw a bigger tetrahedron because we're probably going to mess around with this one a little bit. I hope. So I'll say that 14 is here, 20 is here, and x is here. Okay. So if this is going to be a triangle, one of the things we'll need to have is that x is less than 20 plus 14. But that's assuming x is the longer side. What if x isn't the longest side? That would make 20 the longest side. That would mean 20 has to be less than 14 plus x. Just other things to think about. Now we're getting a lower bound for x. X has got to be at least 6. Okay? So that's certainly limiting our values for x. But what other triangles can we get in here? That's the real question. So, we have the red triangle in here. We'll have a blue triangle over here. We'll have a green triangle over here. And there is a fourth triangle, this outer one. And that's one we have to be mindful of as well. Okay. So we have 14, 20. Those are our two smallest. How about we switch and talk about 70? Where could 70 go? If I put 70 here, I notice that I have 70, 20, and another side length. This has to form a triangle. 70 is clearly the longest length, because x is already spoken for, so the other lengths are 52 and 40, much less than 70. So this length plus 20 has got to be greater than 70. This will have to be 52. If it were 40, 40 plus 20 is 60. That's less than 70. This wouldn't form a triangle. Okay? So that means this one has to be 40. Then we have 40, 14, and 70 form a triangle? I don't think so. 54 is less than 70. That doesn't work. So 70 can't go here. And if we argue symmetrically, we'll realize 70 can't go here either. I think, right? Well, let's see what happens. If I put 70 here, with 14 here, that would have to be 52, 60. No, that's still not enough. 14 and 70 can't form a triangle with the remaining numbers. 14 and 70 would have to form a triangle with x. And that might be something to keep in the back pocket. But that tells us 70 has to go here. And by our reasoning before, that means 52 has to go here. 40 will have to go here. Now 40, 14, and 52, that's fine. That's a good triangle. 70, 20, and 52, that's another good triangle. So we just need to ensure that 70, 40, and x are a good triangle. Now x is at most 34, so 70 is still the longest length here. So we need 70 less than 40 plus x. That means 30 is less than x. And we know x is less than 34. Now this x being less than 6 doesn't really matter. I don't really care about it anymore. But this gives us possibilities. X can be 31, 32, and 33. So we have 3 possibilities. Does that cross anything off on our list? No. The bare minimum was that there were 3 possibilities. But that's, I mean, if we don't find anything else, we'll know that B is our answer. Great. And let's just take another pass at this. We did the 14, 20, and x. That's the case we're working with. We realized 14 and 70 have to be opposites, and that forces a 52 and a 40 here, and that put all our limits on x. Okay. So these three values for x will work, and they will form a tetrahedron. So now, let's look at the case 14 and 20 are opposites. Okay. So 14 and 20 are opposites. Are we ever going to be able to even get a tetrahedron here? So once again, we'll have the red triangle, the blue triangle. We have to be mindful of all four triangles. They all each have to work out. Otherwise, we're not going to get them to come together and form a tetrahedron. And then we have the purple triangle on the outside trying to hide. Okay. So I'll put 14 here. And I'll put 20 here. They have to be opposites. Actually, we'll keep 14 in black as well. So now the question is, well, where does x have to go? Okay. So if 14 and 20 are opposites, that means that one of these four remaining ones are going to be 70. And that means 70 and 14 are going to share a triangle. Okay. So it could be 70s out here. Or it could be 70s out here. Now, it doesn't particularly matter where we place 70 right now. No matter which one of these edges we use, it'll still form a triangle with 14 and 20. So I'll say this one's 70. But 70 and 14, there's no way. I can't put a 52 here. I can't put a 40 here. I have to put an x here. I have to. Otherwise, these guys aren't going to form a triangle. So that tells me, well, either x is the biggest one or 70 is the biggest one. If 70 is biggest, then 70 is going to have to be less than x plus 14. And that means that x is going to have to be greater than 56. Okay, that's possible. And if x is the biggest, then we'll also have x must be less than 70 plus 14. So x is going to be less than 84. It actually doesn't matter. These are all, it doesn't matter who's the biggest, really. These are all just inequalities you get from being triangles. So right now we know x can be between 56 and 84. That's quite a range. Let's see if we can narrow it down. So x had to go here. There's no other number that can go here. And so once again we're left with a 20, 70. This is going to have to be 52 here. Nothing we can do about that. And this one's going to have to be 40. So let's check our triangles. Do they work? Well, 20, 70, and 52, that works. 52, 40, and 14, that still works as well. X, 70, and 14 work if these inequalities are satisfied. And now 40, 20, and x, that needs to be a triangle. So x has got to be less than 40 plus 20. Which is 60. And we also have to have 40 is less than 20 plus x, or 20 is less than x. Okay? So if we were to sort of take a look and overlap, all of these situations, all of these inequalities have to be true in order to make a tetrahedron in this case. So they're all satisfied by saying 56 is less than x, is less than 60. So that means that x can be 57, 58, and 59. So we get 3 more cases to work with. So 31, 32, 33, 57, 58, and 59. That's a total of 6. Is 6 one of our possibilities? Yeah, it is. And I'm pretty confident in it because there's only one other higher possible number it can be, and that's 9. Now, we shouldn't be satisfied there. And what I mean by that is, great, 6. And we got that logically. And if we're down to the wire, it's the end of the question, that's fine. We'll put 6, we're done. It's either 6 or 9. right? It can't possibly be 5. We have 6 cases that work. So it's either 6 or 9. We've narrowed it down to 50-50. I would go with the 6 that we've got, unless you did a little more work and started to realize, oh, there might be another case. And if you think there might be another case, maybe hedge your bets and place 9 if you run out of time. But we've got our 6. I would like to do a little more digging to make myself convinced it's not 9. I'd like to go back and double check, is there any case I missed? Is there any reasoning that was a little flawed there? So there's some inequality I didn't properly flesh out. If I've got the time, I want to make sure. Because with a counting question like this, if I've missed a case, I'm absolutely screwed. It's all or nothing when you bubble these things in, and I want to make sure I get my 8 marks worth. Okay? So I think the answer is 6, but let's just go back and mentally run through it in our heads and see, did I miss any case? Did something not quite work out? Did I forget to take a look at something? So, and this is a great review of how we handled the question. So we had our tetrahedron. We have 4 triangles. 4 triangles, and we've been working with 4 triangles. Now we're talking about the triangle inequality. Okay, great. The triangle inequality should be all that does it. Okay. So we realized pretty quickly with 14 and 20, I can't have 40 here. That's not going to work. You can't have 52 or 70. It would have to be that other number. So we got a case here, 14, 20, and x form a triangle. Either that or 14 and 20 cannot be part of any triangle. Okay, that makes sense. So if they're not part of any triangle, then they have to be opposite on this tetrahedron. And those are the only possibilities. Either they form a triangle or they don't. If they don't form a triangle, then they're opposites. There's no other location they can be. And if they do form a triangle, then they have to form a triangle with that x. Because none of the other numbers will cut it. So we put our 14, our 20, and our x. We did that first case. We got one triangle here. And as long as these 2 inequalities worked out, then we're satisfied. Okay. So that worked out fine. And then we said, okay, let's try and place some other numbers. We tried to place 70, and we realized pretty quickly 70's got to be opposite 14. 14 and 70 won't form a triangle unless they've got that x in between them. So 14 is opposite 70. We actually worked that out. We tried to place 70 anywhere else, and it didn't work. Once we place that 70, we say, okay, well, 40 can't go here, so 52's got to go down here. 40 here. Well, let's just double check. Are these working out? That triangle, the red triangle's worked out, the green triangle worked out, and the purple triangle works out as well. Now that blue triangle, in order for it to work out, 70's got to be less than 40 plus x, and that gets us these 3 cases right here. Great. And that was it. It flowed logically from that point. As soon as we said 14 to 20 and x formed a triangle, that forced 70 over here, which forced 52 here, which forced 40 here, which forced a triangle inequality with 40, x, and 70, and that was the only other condition that really applied. Okay, so I'm confident in our first case. It's only going to result in 3. Our second case, which was the only other case, we've already reasoned that. 14 and 20 are opposites, so we ask, where can 70 go? Well, no matter which of these 4 places we put 70, he's going to form a triangle with 14. And we've already said that that's kind of impossible with the other numbers, 40 and 52. So x will have to go there. So we said x, 14, and 70, that's going to be the red triangle. And in order for that to work, we have to have some inequalities here. We get 2 inequalities here on x. So once we place 70, it forms a triangle with 20, and we're back to square one. Where do we put 52 and 40? 70, 20, and 52 this is the only triangle that's going to work there. Green triangle works out great. So we got green and red triangles. They've worked out fine. 40 has to go up here. 40 is left over. And 40, 14, and 52, the purple triangle is satisfied. Now how about that blue triangle again? X, 20, and 40. Well, we get 2 more inequalities on x. They all have to be satisfied to form triangles, to form a tetrahedron. So we combine them. 56 less than x. That also covers the 20 is less than x case. 60 greater than x. That also covers 84 being greater than x. So x is between 56 and 60. That's 57, 58, 59, and that's it. So that's a total of 6 cases. So we get 6 possible lengths. X is 31, 32, 33, we said 57, 58, or 59. Okay, so our answer is E6. Okay. Now notice when we double checked that, we made sure that the cases did work, that we made sure that all the triangles worked out, because maybe we counted 58, but there was some other triangle inequality reason that it didn't work, and we would have had an answer of D is 5. But we did. We made sure that all the triangle inequalities, narrowed it down, and all 6 possibilities really do work. And that wraps up question number 25. It's a nice little question. I thought it was going to, when I saw tetrahedron, I thought I was going to be a little more three-dimensional geometry, but it wasn't really. It sort of just boiled down to you have 4 sort of linked triangles. And it's just triangle inequality. It was all two-dimensional triangle inequality work. So not a bad question at all, and I think a great way to end the contest. There was some 3D reasoning, but not really a whole lot. And we're confident in our answer of 6. We went through it once, and then we went through it with a fine-toothed comb a second time, made sure, yep, those are the only 2 cases. And when we do those cases, we get this inequality, because 70's got to be placed over here. We get this inequality, because 20's got to be placed over here, and it all worked out. So we do have our 6 answers. Great question, I think. So that concludes the 2002 Fermat paper. I look forward to seeing another contest up here really soon. I think it'll probably, if you're looking for another Fermat, I'll be on to the 2003 Fermat, or I guess 2003 Hypatia is coming up as well. That's a written grade 11 contest. And of course, the next in the sequence will be Euclid. 2002 Euclid, so stay tuned for that. And as always, thank you guys for watching, and I'll see you in the next video for more math.